So, yeah, hello everyone. Welcome back to our weekly discussion sessions for the physics of the nanoscale devices NPTEL course. This is the weekly session number 8. Yeah. So, in this, we shall be covering topics covered in the lectures of week 9 of the course. So, as always, let us begin with uh, by asking from the live attendee if there are any questions or queries that they have. So, Kamal, do you have any queries or questions? Hello.
Yes, sir. No, sir. Right now, I don't have any query.
No doubts. So, you were able to solve the last week's assignment, I suppose.
Okay, sir.
No, like I'm asking, you were able to solve the assignment fine, right?
Actually, in that, sir, one.
Uh
Wait,
huh.
sir. I'm telling.
Yeah,
I'm op- I'm opening assignment section.
sure.
Hello, sir.
Yes.
Sir, question number 10.
Question number 10. So, can you see my screen?
Yes, sir.
Yeah. Okay.
Sir, in the
So,
previous week, you taught
uh
so
huh.
much about MOSFET and then concluded the session with DIBL. So
Yes.
mostly the DIBL effect comes because of the short channel effect.
Yes.
But sir, in that you see that drain induce is observed in dash long channel due to the high electric field in the longitudinal direction.
Uh huh.
Option A is correct.
Can you see my
Sure.
the
Yes,
screen that
yes.
I've shared?
Wait, sir. Wait. Short.
I mean, that's the correct answer.
Yes, sir. Yes, sir. Right, sir.
So, so I hope that part is clear.
Yes, sir. Yes, sir. Clear, sir.
Yeah. Okay. So, fine. Now we shall move on to the contents of week 9. So, week 9, what we shall be doing is, yeah, so let me briefly stop sharing. So, the principal thrust of week 9 is to, so in week 8, we were qualitatively looking at the various aspects. We managed to develop the band diagram picture of the MOSFET device, and then we had inferred that electrostatics in two directions, the x direction along the channel, which is determined by the VDS, the drain source voltage, and the y direction, which is across the gate oxide layer, where the electrostatic shall be controlled by the VGS, or the gate source voltage. Uh, and we found that the behavior of the device will be a combination of these two. We approximately sketched the current dependencies. Some of the graphs I drew last week were intentionally inaccurate. I didn't want to give away too many answers for the assignments. So now, whatever qualitative ideas that we developed, qualitative notions that we developed, we shall represent them in more quantitative terms, so that given a certain set of device parameters, and if I were to say this MOSFET is in the saturation region, what is IDS? the like people who have seen the lecture should be able to evaluate what the drain source current would be under the given conditions for the given values of the parameters. So primarily when you go through the lectures for week 9, you shall notice that bulk of this week would be covered in derivations. So in that spirit, rather than redo the derivations, I shall primarily focus on the lecture slides themselves and highlight what are the important points and what areas people should pay attention to. And we can maybe do one or two questions to see how these things play out. So, yeah. Can you see the PowerPoint?
No, sir.
No. Oh, yeah, I stopped presenting. Yes. Let me start presenting again. Oops. Uh, yeah. Yeah. So you can see this now, right?
Yes, sir.
Yeah. So, uh, let's just one second. Somebody else is joining the call. Oh, Lafayette is here. Perfect. So, hello, Lafayette. So the session is underway. Yeah. So before we start, do you have any questions from the previous week's content, lectures or assignments? Okay, I'll assume there are no questions. If you have any questions, please feel free to ask. Uh, so yeah, starting with this, how do I get rid of this part? Not the previous, it's taking too much of space. Yes. Yeah, this should do fine. So, um, now what are the things here? A letter. Where is my eraser?
Hello, sir.
Yeah,
Sir, one question came into my mind.
please go ahead.
In you saw that in the transfer characteristic curve, there is in the x-axis it's written
Yeah.
like VT.
Yes.
VT, that is threshold voltage. And
Yes.
right now, sir, I am doing some simulation related with graphene nanoribbon. In that, I am getting some high threshold. Like suppose I am taking voltage from 0 to 2 volt for two probe device, like source, drain, and
Yes.
channel. So in that, I am getting VT around 1.6 for
Mm-hmm.
0 to 2 volt. So, sir,
Okay.
my question is how this VT varies, like maybe it is because of material property or maybe some channel length, like
Okay. So now tell me this. Over
yes,
here, like along what direction is this? The transfer characteristics. So what is the voltage that is being varied?
wait,
Like what is
it's
on the
VDS na sir?
x-axis?
Sir, actually it is three terminal device.
No, no, this is a three-terminal device,
Yes,
but along the
it
transfer
is VDS,
characteristics,
VDS sir,
huh?
VDS.
VDS. VDS is varying. Okay, now why aren't things showing up? Ah, okay. So this is also a problem. So I cannot use the presentation mode for this
Okay,
because the doodling will show up first and the slides will show up later. And why am I unable to find an? Oh yeah, here it is. I have been blind. Yes. So let me just erase everything over here so that things become clear. You guys can see the writings on the slide, right? Or do you want me to zoom in? I can zoom in if you want.
No, sir, it's clear.
It's clear. Okay, good. So yeah, just for the sake, I mean, let me just increase the zoom factor by one. Yeah, this should do good. So see, the basic idea is as follows. So over here, we are considering the variation with respect to VGS. Okay, so we are varying VGS with VDS held constant. So
Yes,
these
sir.
are two different curves for two different values of VDS, and as we have seen before, uh, the VDS2 is greater than VDS1. So essentially, higher the VDS, the more current that will flow through my device.
Yes, sir.
However, what should be noticed is VGS is essentially a voltage that is applied in this direction. Okay, it is between this terminal and this terminal. So it's okay, like VGS is a scalar, so it is not applied in any direction. But what I am seeing is the variation of the potential along the y direction of the device. Whereas over here, I am looking at the applied voltage along the x direction of the device. Okay, so this concept of the threshold voltage that we are seeing here, this point, as you can see, this is roughly the same for both VDS values. So
Yes.
first, like one would assume that the threshold voltage is a device characteristic. Is that clear?
Yes, sir.
It's a device characteristic. Like it's not some kind of a biasing point or
Yes, sir.
okay, it's not a selected parameter. It is a device characteristic. Now, what else do we know about the operation of a MOSFET? Like, this is what we discussed last week. Essentially, like depending whatever the mode of operation of the MOSFET is, we are looking for either some kind of a channel inversion or some kind of a carrier accumulation. Correct?
Yes, sir.
So that is triggered by the gate voltage. That is essentially the purpose of the gate voltage. The gate voltage will decide how much carriers are present in between my source and drain so that a voltage applied here can be conveyed via a current to from the drain to the source or vice versa. Right? So this threshold voltage is the point at which that phenomena starts. So what are all the things these things will depend on? They will essentially depend on the like most primarily, since we are looking for availability of charge carriers here, it will depend on the geometry of the channel. It will depend on the Fermi level. It will depend on what else? Uh, will the length of the channel change the threshold voltage? Ideally, it should not, but in a realistic device, it may have an influence, although quantifying that influence might be slightly difficult, it might be non trivial. So, primarily speaking, VT will depend on VT will depend on the like the band structure,
Okay, sir.
okay, of the gate uh, like so it will depend on the band structure, it will depend on the like since I'm seeing the band structure, all the Fermi level and the conduction valence band energies all go in there, and the geometry. So the material properties and the device structure, both of these will determine what my threshold voltage will be. We shall not go too much into the derivations of VT, but we'll certainly see at least one case where we'll see VT reducing or increasing. So that part will be seen
Okay, sir.
probably in the next week. And as I promised you before, next week, and as you suggested, I shall also be presenting some papers that I can, share with you guys, where the concepts that we have been discussing, we can see how they have been implemented in devices, at least for purposes of, simulations, if not actual fabrication. Okay,
Okay. Thank you so much.
so yeah, I mean, sure, that's kind of the job. So yeah, so this is the long and short of what we discussed last week. Added to this was the concept of DIBL. So one small clarification from before. What should be noticed is because of the drain-induced barrier lowering. So again, what should be seen here is uh, how shall we call this? So again, we are looking at the ITS versus VGS relationship. Okay,
Reading.
so again, the voltage that is varying here is VGS. Okay, so I think last week I said this was going to be VDS. I made a mistake there. So uh, this is for VGS. This graph essentially looks like this because this is a semi-log plot. The y-axis is log of IDS. So what is DIBL? It is essentially as we increase VDS, what will happen is, if you remember, yeah, let me just go to the previous slide. So over here, as and when, like, ideally speaking, what I will want is this high point is fixed by the gate voltage, and this slope is fixed by VDS. Like, I want these two things to vary. I want the height of the barrier to be controlled by the gate voltage, and I want the slope of the barrier towards the source side or the drain side to be controlled by VDS. But as we discussed in short channels, especially when VDS is high, the drain voltage will also have an effect on the barrier height, and that is kind of illustrated here itself. So, as and when my drain voltage is increasing, the barrier height is also automatically changing. So, this phenomena is known as drain induced barrier lowering. So, what DIBL will actually do is it will increase the current. Now, increase the current with respect to what? So that is what we can see in this graph here. As you can see, if yeah, so observe this point. Yeah, so this is my threshold voltage. So as you can see from the, as you can remember from the previous graph, like, larger values of current will start occurring only after the threshold voltage. Okay,
Yes.
but what we will see is, for the case of like DIBL essentially. Uh, yeah. So now this is where VDS is VDD, right? Yeah. So yes. So in which case is VDS higher? I mean, I'm asking you guys.
VDS.
Like, in which of these curves is VDS higher?
Top one, sir.
Yes, it's the top one.
Yes.
So you can see that at the same VT, like, so the ideal behavior that we wanted to see is this. Up until VT, irrespective of VDS, the current variation will be roughly the same. The variation in the current becomes apparent only after the threshold voltage. Whereas because of DIBL, what happens is, as you can see from here, at the threshold voltage itself, this particular curve for a higher VDS, the current has increased significantly. But in an ideal circumstance, I would have wanted both of these curves to be very close by until the threshold voltage and then start diverging. But here you can see that they have diverged significantly already. So this is the notion of DIBL. So this essential drift of this curve to the left hand side as the voltage increases is what we call drain induced barrier lowering. Okay.
And sir,
Uh-huh.
in that we also studied that because of DIBL that drain
Yes.
cannot accumulate all the electrons from the source side,
Yes.
and because of that we get the less current.
No, no. Yeah. So, okay, fine. So we get. Okay, now how
That
do
thing.
we? Yeah, no, you're correct. Just 1 second. Yeah, just 1 second. Please come in. Come in. Yeah, apologies for the interruption. Yes. So, yeah. So, yeah, what you are saying is accurate. However, looking at this, it might seem that the current is increasing. So, why do we say the current reduces? That is actually reflected in not in this graph, but in this graph. It is represented in the output characteristic. Now, I mean, you can tell me, okay, tell me this. Where is VT in this curve?
Where
Like
is
in,
VT?
yeah. How can we identify VT? I showed this last week. At least Kamal, you should be able to answer. Like, what is the state of the device below VT?
Okay, sir. Ohmic region, sir.
No, no, no. Like below VT, what is the state of the device? It's off. It's in the cutoff region.
Yes, sir.
So it's somewhere over here. Do you understand? Like, yeah, this is the
Okay,
ohmic
okay, yeah,
region.
sir.
This is the
Yes, sir.
saturation region. Like, these are the different values of VG. VG is increasing as I go in this direction. This is increasing VG. Like VDS is increasing in this direction. As I move up, VG is increasing, and VT is occurring somewhere over here. Okay. Now, what happens because of DIBL? Observe in this. Yeah, observe in this graph. Essentially, as the drain voltage is increasing, the threshold, now see, this is the current I'm supposed to have at the threshold voltage. But unfortunately, because of DIBL, what is happening? This value of current is achieved at a much earlier voltage. So DIBL in essence can also be seen as a leftward shift of the threshold voltage. That implies the threshold voltage becomes smaller and smaller. Is that clear?
Okay, sir.
So now how will this change be reflected in this graph? Now this is the point of the threshold voltage. Now if the threshold voltage has become smaller, what will happen to all of these graphs? They will all move down. Is that clear? This entire
Yes, sir.
bunch of plots will come down by a few units. That implies IDS will reduce. Is that clear?
Okay.
So that is how we say IDS reduces. So when we say IDS reduces, we should understand with respect to what? Like increasing VDS will not give me as much IDS as I previously got when the impact of DIPL was low. Okay. So that is how it is supposed to be understood. One should not directly look at this plot and say, okay, here itself I can see that IDS is reducing. No, it is not apparent in this graph. We should see that. See, this is a transfer characteristics are shifted to the left. Like this is important. This line is important. So this leftward shift is what DIPL is. This leftward shift is essentially a reduction in the threshold voltage. So as my threshold voltage is reducing, like geometrically speaking, VT is over here. That implies VT will occur at an even lower point. Since VT is occurring at an even lower point, all of these graphs will be kind of shifted downwards. So because of that, the relative gain in current is somewhat lesser. But as you can see in today's discussions, we'll like quantify this notion, and you'll understand why the like you'll get an actual formula to see why the current is reducing. Okay, so yeah, so
Here, sir, we haven't shown anything about gate, na?
where
In the previous graph, sir, previous slide,
here,
in this slide. So whatever we are discussing that how threshold voltage changing from VDS2 to VDS1, but
yes,
right now we are not discussing anything about VG, gate voltage.
yeah, we are not like
Yes,
essentially VG is being fixed.
yes,
Like
sir.
for one of these lines, VG is fixed.
Hmm.
Okay,
Okay, sir.
yeah, VG is not being varied, but VT is being shifted because of the variation in VDS.
Okay, sir.
Okay, VG is not being varied, but VT is shifting. Remember, VT is a constant, it's a device property.
Yes, sir.
Because of the short channel effects, the device property is getting modified. And that is a non ideality. I do not want that, but it is happening in a realistic device. Is that clear?
Yes, sir.
Yeah. All right. So, moving on. Yeah, so another parameter that we should remember is this quantity known as the subthreshold swing. So this is essentially the change in this gate voltage, this shift that we are seeing with respect to the increase in the current. So ideally speaking, we will want this quantity to be as small as possible because uh, that implies with a very small change in the gate voltage, we can get a very large change in the current. Is that clear?
Yes, sir.
Like the subthreshold swing is the inverse of this slope. So we want this slope to be as high as possible. That is, for a very small change in VG, I need a very large gain in current. Essentially to switch it from the off state to the on state. So if the slope of this is high, the inverse of the slope will be small. So yeah, and typically we will want, oh, okay, fine, yeah. It should also not be too small because if it is too small, then external noise will also randomly trigger my device from the off to on state. So typically we will need a minimum value of around 60 millivolt per decade. that is the accepted, like it's a standard value that is accepted as a minimum for the subthreshold swing. We would not want the subthreshold swing to be too high, but again, we don't want it to be too low. This is the lowest value. And as you guys might know, voltage fluctuations in the millivolts is accepted. Any fluctuation that is below the order of millivolts will fall into the domain of thermal noise or other kinds of fluctuations, which in principle cannot be controlled by us when we design and operate the device. So yeah, this part is important because this discussion here will play an important role in our subsequent derivations. So let me just get rid of all of this stuff. And don't worry, whatever I'm writing in these slides, I shall share with you guys. So yeah, this is the yes. Now we are looking at the three-terminal device schematic diagram from the two-terminal device. So we are assuming that the source is grounded, therefore we have a VDS and a VGS. So this is the approximate band diagram from the source through the drain. So yeah, so this is the, oh, it's a bit too thick. You will fine. Yes. Okay. I'll just went silent. You guys can hear me, right?
Yes, sir.
Okay. And yeah, in case my voice is dropping or anything, please let me know because there seems to be some kind of a network issue on my end. All right. So yeah, so this is the source end, this is the drain end. The height of this barrier is determined by, so essentially this point is, ideally speaking, I want this to be, wow, you need to be thin. Yes, so I want the height of this barrier to be influenced by VGS, only VGS. And we want this slope to be influenced by VDS. So the things that have to remember is when VDS is small, this slope can be assumed to be linear. Okay. So over here I can say that for small VDS, slope is, why is this thing changing color? Oh, okay, this is one of those gradient things. Oof. Uh, yeah, you stay blue, please. Yeah, this color changing business makes it look hideous. So over here, yeah, ideally speaking, I will only want the influence by VGS, and over here, like for small VDS, implies linear slope. So, what can you tell me if this slope is linear? If this line is linear, what can you tell me? Kamal, Lakshmikanta, can either of you comment on that? I mean, it's in the slide, but I'm asking you guys. I'm not going to tell you where in the slide it is. At least if you can read the slide and tell me what happens, that would be nice. If this were to be some kind of a straight line, if this were to be something like this, then what can you say about
So if you are telling it is linear, then electric field also remain constant in that.
exactly? So that is this point. The electric field is approximately constant. Okay, so that is for low VDS and high VGS. And that is the case where things behave in a way that we can control, because under a constant electric field, remember, for classical transport under a constant electric field, what is the current? Is it a constant? Is it variable? Classical transport model. Any guesses? So, what is the formula for classical mobility in a conductor? What is mu? Do you guys remember this?
VDE, sir.
Huh?
VDE.
What is V?
VD voltage and like electric field D.
V is voltage.
Drift
Or is it
velocity.
something else? Ah, it's the drift
Drift.
velocity. You're correct. Yeah. So essentially, so what is mobility with respect to, like what I'm trying to ask is, okay, forget mobility. How will you write current in the classical model of transport? What is I? Is this correct? Tau upon M, where this tau is the relaxation time. Hmm? And N is the charge carrier concentration.
Okay, sir.
Like this is correct, right?
Okay. Yes, sir.
Because Q times E will give me the force, QE by M will give me the acceleration, acceleration into the relaxation time will give me the drift velocity, that into the carrier concentration should give me the total current,
Okay.
right?
Yes, sir.
Yeah. So from this, can you tell me what the mobility is?
VD equal to
Like, how is mobility related to the current? Just guess. This is
Directly
technically the
proportional.
current density.
Directly proportional.
So J, okay. So what is the other quantity that multiplies with mu? J equal to mu times what? It's mu times the electric field.
Q M E Q upon M.
Huh? No, like this is the relationship. Mu is the
Yes.
mobility and the electric field. Like J is mu times E. Therefore, mu will be everything other than E in this quantity. It will be N Q tau by M.
Yes, sir.
Okay. So now, if E is constant, then J will also be constant throughout the channel. Is that clear?
Okay, sir.
So that is what I would ideally want. I would not want the current to also fluctuate in my channel, because if I have a rapidly fluctuating current, that will lead to other non-ideal effects. I do not want that, because remember, in our ballistic transport, the electron suffers no collisions in the channel. If it suffers no collisions in the channel, the velocity of the electron cannot change. If the velocity of the electron is not changing, the current can also not change in the channel, right?
Yes, sir.
So if we want those things, I would want an approximately constant electric field. However, that is not always possible. If I reduce the channel length, then all of these, drain bias effects and all of these things will start showing up over here itself. So those are the things we will want to avoid. How to avoid them, we will see that later. So yeah, these are the things, these are the most important things you'll have to remember right now. So as you mentioned, Kamal, last week, since we have like a metal oxide semiconductor layer and we are applying potentials and whatnot, of course there is going to be a capacitance.
Yes, sir.
Okay. So now we shall discuss what the capacitance is. So where do I expect the capacitance to occur? Most straightforward.
Between the gate and channel.
Exactly. So I will want the capacitance to occur somewhere between here and, oh yeah, okay, it's fine. Yeah, somewhere between here and here.
Yes, sir.
Correct.
Yes, sir.
So I want the capacitance to be in this region. So what kind of a device is this? What kind of a capacitor geometry is
It
this?
is electrostatic capacitance.
Yeah, it's an electrostatic capacitance, but what kind of a geometry? Like there are different geometries of capacitors. I have parallel plate capacitors, cylindrical capacitors, spherical
Parallel plate, sir.
capacitors. This
Parallel
is
plate.
parallel plate.
Yes, sir.
Wonderful. So I know the formula for the capacitance of a parallel plate.
Hmm.
It is epsilon by D.
Yes, sir. Epsilon naught A upon D.
Yes.
Hmm.
So capacitance per unit area is epsilon by D. So T ox is the oxide thickness and epsilon is given by the dielectric constant of the oxide into the permittivity of free space. So this is the capacitance per unit area. Okay.
Yes, sir.
So that is wonderful. Now, yeah, when will charge accumulation begin in this device? So for this, we have to go back to our classical MOSFET, like our old MOSFET theory that we have read in the uh, probably in your bachelor's. So this is my metal Fermi level. Uh, let me draw this slightly straighter. So I have, yes. So now this is a three level device. Will this be okay? Yeah, this should be okay. So now I have my, okay, somebody else is joining us. Uh, wait, yeah. Welcome to the new attendee. If you have any questions, please feel free to ask. Uh, where were we? Yes, we were here. So, this is my new metal, and I will essentially have, yeah. Now, on this side, what is the nature of my body here, the channel? It is a p-type material, correct? Do you remember, Kamal?
Yes, sir.
Yeah, so there's a p-type material. So, yeah, I shouldn't have written it too far away. Yeah, so this is, yes, this is p-type over here. So if it is p-type over here, where will the, like, so let us say my channel Fermi level is somewhere over here. The valence band will be here. Oops. The valence band will be, I mean, it'll be there, but it will not rise or anything. It will be flatter. So yeah, valence band will be over here, and the Fermi level will kind of be over here, and the conduction band will be at some point. Now, because of the like equilibrium behavior, we will have band bending at this point. You guys, I hope you guys know that.
Yes, sir.
Yeah, so I will have, and for all intents and purposes, the barrier, the insulator here acts as a barrier, like at least in the band picture, because the insulator's valence band itself is like out of reach. So the conduction band is never exposed. This is just a fully filled valence band. No electrons are available. Uh, and So under equilibrium considerations, what we will have is essentially the picture of band bending. So my Fermi level will kind of bend like this, and then my valence band will be close to that, and then my conduction band will be above that. Now, by increasing the voltage, I can lower this to the point where inversion occurs. Are you guys familiar with that?
Yes, sir.
Hello. Yeah. So what happens in inversion? Like which of these bands crosses the Fermi level? I mean, I'm kind of sketched it already. Like if I apply BGS, which way is my band going to bend further? Like, will this go up or come down?
Down.
Come down. Like, this is my gate. This is my oxide and this is my source. VGS is going up. Again, if you're confident with your answer, you can repeat it. It's fine. I'm just labeling things for clarity.
So VGS is how much volt? Positive or negative?
VGS is positive. It's increasing in the positive direction. Oh yeah, like this is the connection schematic. Source is grounded and VGS, so gate gets the positive terminal and drain also gets the positive terminal. So this is the convention. Yeah. So now tell me. Essentially, what I'm doing is I'm increasing the voltage on this side. If I'm increasing the voltage on this side, what will happen to this Fermi level? It will kind of keep moving down, correct? Oops. Okay, that's fine. Uh, yeah. So what will happen to this line? Will it go up or come down? Come on, this should be easy. I'm saying I'm applying a positive voltage to this side. Voltage on the source side is 0. If I'm increasing the voltage, what will happen to this line? Will it go up or come down? Can you guys hear me? Hello. Yeah. Can you guys hear me now? Hello. Yeah. Hello. Can you hear me? Yeah. Can you guys hear me?
Yes, sir.
Okay. So two things have happened. First, yeah, of course, I've been disconnecting and reconnecting. And during the last stretch, when I had to disconnect and reconnect, I paused the recording so that I could talk to myself while sorting this issue out. And I forgot to resume the recording when we have been speaking for the last 15 minutes. So the video is going to be shorter. I cannot roll back time. So yeah, I apologize for the people who are viewing the video. You'll know why. The slides will be shared, and I will, make more annotations on the slides before uploading them. So whatever has been discussed here will be written in the slides. So please read the slides, and you will understand the essential points that we have discussed. And to aid for this, I will also, in the end of today's session, I will summarize everything that we have discussed so far. So yeah, I am resharing. Are the slides visible?
Yes, sir.
Good. So now in yes. So yeah, so this part, like this formula that we are starting with. Yeah. So this formula that we are starting with for IDS. Now this is essentially obtained by assuming diffusive transport of electrons in the channel. Okay. So we assume that there is a particular charge carrier concentration at a point X, and at a point X plus delta X, the charge carrier concentration changes. And we use that, and the potential to obtain this formula, the derivation of this would have been done in lecture 42. So when you see the videos, you will see that. Uh, yeah. Lecture 42 or 43 or like whatever, like the second lecture of week 8. So that should be 44, I guess. So we essentially start from this relation, and what we will remember is that this particular quantity is equal to essentially the voltage at a position coordinate x into the electric field that is in the x direction. Like the voltage is along the y direction, so that is Vg minus Vt minus Vx, and then we have dV by dx. So this will kind of give us a quadratic equation in terms of Vx, and using that we can essentially like solve this for different approximations. So the general result is Vx will look something like this. It will be Vgs minus Vt times 1 minus square root of 1 minus 2 Vgs minus Vt into Vds minus Vds squared by 2 divided by Vgs minus Vt the whole squared into x by L prime, where L prime is the point where the pinch off is occurring. Okay, so this is the general model. However, of course, when VDS becomes small, the potential profile becomes linear. So in that case, like essentially this 1 minus square root of x, this whole quantity will become essentially 1 minus x by 2, and substituting the values, you will see that all the potential values cancel out. So this is the general expression for Vx. So this is what is substituted in oh, the derivation is actually done in this slide itself. No, it's not. So yes, in general, when I write hello, am I audible? This is most troublesome. Yeah, can you guys hear me now? Hello. Resume recording, and yeah, so we are back essentially. Again, for clarification, what was the last thing you guys heard me say? Okay, so it's that bad. All right. So let me just start with this. So in general, from like the previous set of slides, we saw that we can write this as VGS minus VT minus Vx. We can do this, correct? Right?
Sir, please share the slide.
Oh, okay. I have not shared. Yes, thank you. My entire screen, please. Yeah, is this visible? Yeah, should be. Correct? Like, is what I've written in blue here accurate? Let me rewrite it. So this is the charge in the ideal situation. However, when we have like gate effects on the channel, not gate effects, drain effects on the channel, Qn of VGS comma X is equal to minus C ox into VGS minus VT minus V of X. Is this correct?
Yes, sir.
So this is the charge that is available at a particular point X along the channel. So that charge into like the applied electric field times whatever relaxation time and divided by mass will give me the current. Therefore, the mobility will essentially vary depending on the local charge carrying concentration at this point x. So using that and the diffusive model of transport, we can derive this expression for the current in the drain source in the channel, assuming that pinch off is occurring at some point L equal to L dash. So from there, we can use the following relation to essentially solve a quadratic equation in Vx to give us the general representation of Vx. So this formula that you see here in the box, this is the general representation of Vx as a function of Vds and Vgs and Vt.
Okay,
So
sir.
typically this is a complicated relation, but for various approximations we can write different versions of the formula. When Vds is very small, I can neglect this Vds square term. So what we will be left with is this, because this Vgs minus Vt and Vgs minus Vt will cancel. So I'll essentially have Vgs minus Vt into 1 minus square root of 1 minus 2 Vds divided by Vgs minus Vt into x by L prime. Uh, I can further do the binomial approximation and come back to our original ohmic limit, or I can leave it like this to observe the non-ohmic effects. So this is for small drain biases, like this is still close to the linear region. If you want nonlinear effects also, in the model that we are considering here, this is the general expression. Remember this will be important. Again, when you go through your lectures, focus on this part. Now, after this, we shall now essentially, yeah, this part is not required. You can like safely ignore this. Yes, this is important. So now, so that was the variation of Vx. But now we shall look at what is happening in the y direction. Like so far, we have simply been saying that there is C-ops, and because of the oxide capacitance, I have some charge accumulation, and that charge contributes to my electron, like my current in the channel. Like that is what we like have been stating. But for like typical devices, I cannot model this entire interface by using just one capacitance parameter. That is not a valid expectation. So there may be other effects also. So in general, to analyze that, we will have to do what is known as 2D electrostatics, because now I want to know what is the impact of VDS on the the y direction also. VDS is applied along the x direction, but we know that effects such as DIBL exist. So because of that, ideally speaking, I would want to study the charge concentration as a function of VGS and VDS. Kamal, you might remember last week, this was the general charge expression that I wrote for a MOSFET. So we
Yes,
want to
sir.
find out what this is. So
Also
how
the
do we,
velocity.
yes,
Yes,
into
sir.
the velocity, of course. So how do we do that? So we do that by starting with the Maxwell's equations. Okay, so this is the first Maxwell's equation in matter, where we say divergence of the displacement is equal to the free charge carrier concentration in XYZ. Of course, this is a 2D system, so we will not be worrying about the Z coordinate. Everything will be in terms of the X and Y coordinates. This can further be written in terms of the potential. So psi here represents the potential. Okay, this is not the wave function, this is not some other quantity, this is the potential, which is the voltage. This is the localized voltage at a point along the device most preferably somewhere along the channel interface, okay, along the oxide body interface, which comprises the channel of my MOSFET device. So now that is the equation which we use to do the 2D electrostatics. So in order to do that, we have to like remember, yes, we have to remember, what shall we say? No, yeah, this slide does not say much about that. So just like remember that this equation is essentially how we shall solve the complete behavior of the MOSFET device, because now this potential is no longer just VGS or VDS. This is a combined function of VGS and VDS. So it will vary as I'm moving along both the X and Y directions. And because of this variation in the potential, there will be a variation in the charge carrier concentration. And by using the other Maxwell's equations, I can also find the current density in this channel. But of course, right now we are only concerned, but solving that entire system of Maxwell's equation will be computationally non-trivial. It will be very difficult. So what we will essentially do is, we will use the electrostatics to obtain the charge carrier concentration. And once we obtain the charge carrier concentration, we will come back to our Landauer approach to transport. Is that clear? So this is how we are going to model the behavior of our device, especially for short channel devices where we can assume the channel to be ballistic.
Yes, sir.
Okay, because at short channels, of course, diffusive transport is not present. We can assume that the carrier transport is ballistic. So step one will be to do the 2D electrostatics. Step two, we shall be using the Landauer transport, and I think this is the basic idea. Okay, so derivations on this will be present in the lectures, but there will not be any questions based on the 2D electrostatics. However, I urge that you guys listen to this lecture because concept wise it is important. If you have any queries regarding this, you can post it on the forums, or next week when we meet again, you can ask me questions and I will tell you how these things are done. So now I just want to give you a rough idea of how these calculations, like essentially how do we simulate the device. Like later on, if you are working with short channel devices, this is an approach that you guys can take over. I mean, take up. Like the potential profile and the charge carrier distribution is determined by the classical electrostatics, and after that we use our semi-classical or partly quantum mechanical treatment of Landauer transport to calculate the current through this three-terminal device. So this is where the two-terminal device theory that we learned previously combines with the three-terminal picture of the MOSFET. So that is why I am kind of repeating this point over and over again to emphasize the fact that now we shall be incorporating the concepts that we have been learning throughout the first half of the course into the framework of the three-terminal MOSFET device. Is that clear?
Yes, sir.
Yes, sir.
So go back and look at your MOSFET current equations and integrals. There are one or two questions based on that in the assignment. Just look at them. Okay. So that brings us to the end of these slides, and after this, I think I will jump to the last section before summarizing. So, which one will that be? I think that will be this one. Is it this one? No, it's the next one. It's actually not even this one.
Hello, sir.
Yeah.
Any suggestions for exam?
Meaning?
Maybe on 30 April we have exam for this
Yes.
subject.
Yes.
So any suggestion to give 100% in this exam? Like,
Oh, we'll do that. Like, so as you are seeing, like we are already in week 9.
yes.
So 3 weeks from now, we'll be done with the course lecture. So after that, I will still be taking 2 more sessions,
Okay, sir.
or at least 1 more session. So in that, I will talk about the exams explicitly.
Okay, sir. Okay.
Okay, so I'll tell you guys like what areas to focus on, how to focus on. So right now, what I'm saying also applies for the exam. What you're supposed to understand, of course, alongside of the formulae, like so. Remember this case that we saw. So I was talking about the yeah. So this entire electric field versus position in the channel. Now you need not remember the exact formulae that are occurring here, but kind of see how the things depend on say VDS or VGS. Try to get a conceptual feel of it. Like we will not be asking for exact formulae or exact, like we will not be testing your memory. What we will be doing rather is, even if there are numericals, they will be based on relatively simple concepts. So, okay, as a hint, let me just open up the assignment for the upcoming week. I'm not going to solve the question, but I hope you can see how that question will be should be approached based on what we have discussed so far. So, yeah. So look at question 5. Can you see that? Hello.
Yes, sir.
Yeah.
Yes, sir.
So over here, VGS has been given, VT has been given, thickness of the oxide layer has been given, the area has also been given. The what to say, like dielectric constant, like essentially the permittivity of the medium is presented, and you've been asked to calculate the charge in the channel. Do you have all the information that is required? I'm not asking for the answer. Please don't solve the question. I'm just asking, do you think you have all the information that is required? Do you think based on what we have discussed in today's lecture, I mean today's discussion session, you can answer this question?
Yes, sir.
Kamal, what about you?
Checking, sir.
Sure. Uh, Again, don't have to calculate and tell me the answer. Please don't tell me
Yes.
the answer. Uh,
Sir,
yeah.
it has already been week 9.
Yes.
So while going through the lecture videos,
Yes.
now I am understanding that
Yeah.
the when we are decreasing the channel in nanometer scale,
Yes.
your kind of the drift diffusion model, which was
Yes.
previously being used, is
Yes.
no more used.
Of course.
It just breaks down.
Yes.
So now in the ballistic case, all
Yes.
this physics that we are learning, that
Uh-huh.
different kinds of mode or the
Yes.
conductivity,
Yes.
and the next week also we will be reading about those how it is applicable to a ballistic case in a nanometer scale.
As you
So
can see, yeah,
yes,
like
yes,
week 10 is
yes,
all ballistic MOSFET.
yes,
Yes.
yes, yes, the ballistic case.
Hmm.
So in the nanometer scale, I'm kind of a PhD scholar working in FinFET.
Uh-huh.
So, so for me, it is kind of new thing.
Uh-huh.
because even through my masters also I have never heard
Hmm.
that we are always heard about this classical derivations only.
Of
But this,
course.
yes, but in the nanometer scale, the
Mhm.
electron kinds of behave like quantum waves. It is so.
So right now we do not consider that, because when we say ballistic, we assume the electron to be a classical particle traveling without any collisions or scattering.
Okay,
The
sir.
wave picture will essentially come when we are looking at devices that are below the essentially the 10 nanometer limit or the 7 nanometer limit. Below that, even the ballistic model will break down. So this quantum mechanical wave, like essentially the pure quantum mechanical treatment that you are talking about, occurs at around the 5 to 7 nanometer limit.
5 to 7 nanometer is the current channel working. Intel is working on it.
Yeah, it's working on it, but it's not yet out in the market, right? So
Okay, okay, sir.
14
Okay,
nanometer is what is out in the market. So ballistic transport will work up to 14 nanometers. 14 nanometers, it is good. If you remember, we did the de Broglie wavelength calculations in our previous discussion sessions. You were there for that. So we saw that the de Broglie wavelength for like typical electron kinetic values or kinetic energy values comes to be around like 15 to 20 nanometers. So something in that range, ballistic transport still good.
okay, sir. Okay, sir.
Yes, Intel and a whole bunch of other people are working on the 5 nanometer domain. So there, ballistic transport models will no longer be applicable because of the like most straightforward reason that the channel will now contain like maybe a few dozen atoms.
Yes,
Like
sir.
at 5 nanometer, the channel will contain maybe 30 atoms. So when there are only 30 atoms, I cannot talk about that system in terms of conductivity, or I cannot talk about resistance or even current for that matter of fact. So over there, I have to treat it as some kind of a potential barrier, and I have to look at the transmission coefficient. I'll have to treat it as some kind of a tunneling problem.
Yes, sir.
Like even when there is, like, you might have heard of these things, even when the barrier potential may not be sufficient, what will happen is some electrons will tunnel through. So there will be like a baseline tunnel current, and like that will be kind of like a background current.
Yes, sir.
So quantum mechanical effects will start manifesting in that form. But for our present analysis that we are looking at, we are staying away from that, because right now we are still like we are not going to the absolute cutting edge. What we are looking at is the general short channel devices, which is actually up to the point of FinFET technologies in truth.
Okay, sir.
Like, I mean, just out of curiosity, like I'm asking you, correct me if I'm wrong also. Like, are FinFET devices single gate devices or multi gate devices?
FinFET devices.
Huh.
FinFET devices can be
Multi-gate.
multi-gate device. Yes.
Like, typically they're multi gate devices, right?
Yes, multi-gate
Huh.
device.
Yeah, because like I essentially throw the gate as a fin,
Yes, it's
right?
the planar structure has been discarded and now it has been
Yes.
to a 3D model.
Yes, so we are doing the 3D structure. So essentially, since we are doing a fin type growth over there, it is a multi-gate device. So the aim of this course is to understand structures like that. Now, why are we doing that? Like, you can ask, it is not the current state of the art that is being practiced by the industry leaders, but the fact is, as you have mentioned, most students, even up to their master's level, only know the classical MOSFET, which
Yes,
is
sir.
like pre CMOS. Even in
Yes,
CMOS,
sir.
that theory is not very completely applicable.
Yes, sir.
Okay, so now the transition has to be made gradually. So maybe 3 4 years of students studying nanoscale devices. Maybe then people can essentially go below the sub, like essentially enter the sub ballistic regime and start with pure quantum mechanical treatment. But as far as this course is concerned, we will not be doing the pure quantum mechanical treatment. We'll be sticking only with the ballistic treatment of the devices. Okay.
Okay, sir.
Yeah.
Okay. So this
So.
kind of physics that we are
Uh-huh.
reading will be applicable when we are modeling the device using some kind of
Yes.
software platform like
Yes.
Synopsys.
Yes.
Then we will need this physics that we were
Yes.
using like modes, transmission.
Yes.
Uh, that's what my doubt is that this physics will be applicable when we are modeling the device,
Yes.
and this physics will be required there. Am I
Yes.
correct, sir?
Yes, yes, of course, you're correct. Like the physics will be required in the device modeling and also for, like subsequent analysis.
Okay, sir.
Because again, once you have developed this model, as I told you before, you can no longer use the conventional current voltage relationships.
Yes, sir.
So what you see as a voltage and a current from the macroscopic perspective will be written as some wave function with some reflection transmission coefficient in the
Yes,
quantum
sir.
mechanics language. So even in the device operation or simulation, those parameters will take the place of our classical current, resistance, conductance, and like resistance quantities.
Yes, sir.
Okay, so it
Yes, sir.
will substitute in both places,
Yes, sir.
and we will be like rather than talking about the Fermi level, we will be talking about the concepts like what shall we say that? Yeah, because there are only a few atoms, like statistics will also not apply. So the concept of Fermi level will become irrelevant. So since the concept of Fermi level becomes irrelevant, what we will be talking about are the direct occupation energies of the electron. We'll be referring to the actual electron occupation levels. So to familiarize with yourself with those things, you can maybe look at some quantum dot based devices, because the behavior of quantum dots is essentially like it is quantum mechanical. So even when we apply an external control voltage through gate terminals and several configurations of gates and whatnot, the behavior of the quantum dot device itself is always going to be quantum mechanical. So that kind of a language will be used for transistors also when we go to the like below the ballistic regime. I
Okay,
hope
sir.
that kind of answers your question.
Okay, sir. So my
Okay,
last
so
question is
yes,
not regarding
please.
any
No, no,
studies.
please,
Just,
please. Go ahead, go ahead.
just, just a simple question.
Hmm.
So, is quantum mechanics a difficult subject or an easy subject? Just.
Ah,
Oh,
okay. That actually depends from person to person. It is, how. Okay, so since you are asking a question, I will rather stop sharing and come back to the call menu. So yeah, quantum mechanics. I have personally, I have never found it to be difficult. I have found it to be interesting and sometimes conceptually, non-trivial. Like there are some subtleties that you have to observe. Like when we like essentially talk about quantum mechanics, and we use things like wave particle duality, or when we say there is uncertainty or things like that, they should be understood within a certain context. And as long as people are understanding things within that context, understanding quantum mechanics should not be too difficult. Like what, in my opinion, what people should remember is that quantum mechanics is not something new that we are adding to our understanding. All matter that we see, be it in electronic devices or in and around me, like everything that you can see behind me or me myself, my own composition,
yes, sir.
is all built and constructed according to the rules of quantum mechanics. So,
Yes, sir.
in fact, up to a certain point, the classical behavior that we are seeing will also have its origins in the quantum nature of matter. Like the most standard example that we can cite for that is the behavior of your conductors, semiconductors, and insulators.
Yes, sir.
This is a macroscopic, classically observed, phenomena.
Yes,
Why
sir.
are certain materials conductors? Why are certain materials semiconductors? Why are they insulators? To truly understand this, you need to know the electronic configurations of them. To understand the electronic configurations and like essentially their 3D lattices. To understand the electronic configurations and the lattices of these atoms and these crystals, you need to know quantum mechanics. So it is actually the combined cumulative effect of quantum mechanics that even gives me different kinds of conductors. So
Okay,
as
sir.
long as you remember these things, um, studying quantum mechanics will be relatively easy. Like, I'm not saying it will be trivial, but you should keep reminding yourself that quantum mechanics is not some alien knowledge that we are introducing into our, current knowledge base to totally radically change it. We are not doing that.
Okay.
Essentially, what quantum mechanics does is whatever we know to be true, it will explain it in a slightly more refined fashion. That is all. What we know to be true will never change. Like, as you have seen and will continue to see, even a ballistic MOSFET has cutoff saturation and linear regions.
Yes, sir.
Even a ballistic MOSFET will have all the properties that you observe in a classical MOSFET. So going to the quantum regime does not change the MOSFET into something else. The MOSFET
Yes, sir.
still remains a MOSFET. Only the nature in which we are analyzing its current voltage relationship and transfer characteristics and things like that will change slightly. So
Yes, sir.
as long as you are okay with making those subtle shifts, understanding quantum mechanics will be easy.
Yes, sir.
Like,
Yes, sir.
don't be too intimidated by it and treat it as something that is totally out of your purview. Usually understanding or analyzing concepts of quantum mechanics it is just a matter of perspective. Okay, so having said that, and since we are also like kind of overshooting on the time, what I will quickly do is I will summarize what we have discussed so far. Like, these are, insofar as our discussions go, these are the important points that you guys will have to remember. So first is like the notion of DIBL and subthreshold swing. So I hope you guys remember that part of our discussion. Drain induced barrier lowering is seen as a leftward shift of the voltage current characteristics, especially, not especially, but like, to be precise, the VGS versus IDS curve will shift to the left. Insofar as the VDS versus IDS curve, in the presence of drain induced barrier lowering, these entire set of graphs will kind of move down, effectively reducing the current gain that we get with increasing the drain source voltage. And the threshold voltage, as was asked, is typically a property of the band structure which comes from the material and the geometry of the device. So the geometry aspects you will see later on. Uh, so that is a part. There is also this notion of the subthreshold swing, which is essentially the variation of the drain source current with respect to the gate source voltage. Ideally speaking, we will want the subthreshold swing to be small, but it should not be very small, because in that case, any kind of inherent fluctuations might also trigger a transition from on to off or vice versa in the device. So the minimum allowed value of subthreshold swing is 60 millivolt per decade. Like, this is an adopted standard. So just remember this value. After that, we have this, like, we have tried to develop the notion of ohmic conductance in a MOSFET. So we will have an ohmic conductance when the potential profile from the source to drain is roughly linear. And since it is linear, the electric field can be seen as constant. Since it is constant, we can use the Ohm's law to represent the conduction in such a channel. However, that is only valid for a small range of VDS, as seen in this curve. The ohmic region occurs for low values of VDS. As and when VDS increases, we move out of the ohmic region. These are the relationships that we have for our current, like, so in the classical limit, yeah, before that, in the classical limit, we can analyze the charge accumulated in the channel through the means of the oxide capacitance, which is essentially the gate capacitance. The expression for Cox is given by this.
Sir, are you
And,
showing something?
oh my god.
Actually, you are
Okay. Yeah, I
showing
have
us.
not shared. I know. I just realized that. I've been talking for 5 minutes. Okay, fine, but the video
It's
will
okay,
have
sir.
it. Don't worry.
It
It's
is
okay,
a
sir.
bit general, sir.
We
Yeah, yeah.
we
The
can
the
we can
video is
understand, sir.
catching all of these things, but no, I will like. Of course, you guys are in the call, so you, you should yeah see the whole thing now. Uh, yeah, you can see it now. Correct? Can you see
Yes,
the
sir.
slides?
Hmm.
Yeah. So these are the formulae for like essentially we are talking about the oxide capacitance, and the oxide capacitance will determine how much charge is present in the channel, and that will in turn control how much current is flowing through the channel. So in the linear region, the current IDS is given like this, and of course to be expected, since it is in the linear region, IDS is directly proportional to VDS. So from this you can also kind of uh, develop a notion of channel conductance. I'm leaving it to you to figure out how to calculate the channel conductance for this. There may be questions based on that. There is the notion of velocity saturation, which I have briefly discussed earlier. So, for very high electric fields in a long channel device, the velocity of the electrons in the channel saturates. So, in that case, we will have this kind of an IDS where instead of having a linear dependence on VDS, IDS no longer depends on VDS because we have reached the saturation point. So IDS becomes roughly a constant. Sorry. IDS is roughly a constant. But this model of velocity saturation should not be considered for short channel devices. This is only for classical long channel devices. And even in that, it is for devices with channel lengths greater than 1 micrometer. Okay. So typically speaking, pinch off is analyzed by incorporating the effects of the drain source voltage on the potential in the y direction. So we represent it as such, and these are the typical expressions for long channel MOSFETs for the current and voltage relations, and so this is VGS minus VT. Yeah, yes. So this is for the long channel devices where pinch off is occurring at some point L dash. So that is material from this slide. After that, we have seen the yes, yeah. So after that, I briefly showed you the derivation of Vx, that is the x dependence of the voltage that is observed in the y direction. And we managed to, like I showed you, that there are several approximations we can make here. And in general, Vx looks like this for small VDS. It can further be approximated using the binomial approximation to get the proper linear voltage profile that we had originally seen for ohmic relationship. Yeah, one more thing I forgot to mention previously is that for the pinch off criteria, VDS must be equal to VGS minus VT. This you guys might remember from your devices, semiconductor devices course, that pinch off occurs when VDS is equal to VGS minus VT. So substituting those values, you can also find out what like Vx would be at those points. Like, I mean, you'll find out that Vx will essentially come out to be 0, because if VDS is equal to VGS minus VT, then uh, sorry, Vx will come out to be VGS minus VT, and the difference of those two will come to be 0, and therefore the charge accumulated at that point will come to be 0, not the voltage. The charge will come to 0, and yeah. After that, the basic analysis of the devices. So how are we going to go about performing the analysis of our short channel MOSFETs, our ballistic MOSFETs? First, The potential profile and the charge carrier distribution will be obtained using 2D electrostatics. So once that potential profile has been obtained, we shall use the Landauer transport to understand how the current conduction is happening across the channel with that particular potential distribution and charge carrier concentration. So that is how we generalize our two terminal device picture to the three terminal picture that is required to study devices such as the MOSFET. One last thing before we end this session. In these lectures, you would come across, you know what, I'll show you in the course page itself. So, yeah. So in this lecture, transport 2, yeah, you'll come across this quantity called the unidirectional thermal velocity. Now this is a slightly important quantity. Remember this, concentrate in this part of the lecture because this quantity will be connected to this notion of velocity saturation that we shall be seeing. Like as I told you before, the previous picture of velocity saturation that I described is only true for long channel devices. In short channel devices, that model does not apply. However, if we can understand the notion of unidirectional thermal velocities, then we can use that to redefine the concept of velocity saturation. Velocity saturation also occurs in the case of I'm presenting, right? Yes, I'm presenting. Velocity saturation also occurs in the case of short channel devices. This quantity is important to understand that. Please pay attention to this part in the lecture because that will be important for the subsequent weeks, like subsequent weeks content, and even maybe for one or two questions in this assignment itself. So with that, I think we can end today's session. I sincerely apologize for the poor quality of presentation and any discontinuity in the recording that you guys might notice. That was due to persistent network connectivity errors on my end. I hope it will not happen next week. I will see to that it doesn't happen. I'll probably connect using my personal Wi-Fi from the beginning of the call itself. So, yeah, with that, we come to the end of this week's discussion session. I would like to thank the live attendees for putting up with this session, especially today, considering the technical difficulties that we've been having. And uh, also would like to thank anybody who is viewing the recorded versions of these discussions. With that, we bring today's session to an end. We shall meet again next Saturday from 3 p.m. to 5 p.m. I thank you all for joining me, and
Thank you,
I
sir.
am ending the call. Yes.
Thank you, sir.